Alright guys, so today I want to talk about how magnetic fields can be used to cause a projectile motion-like movement of charged particles. And so what I mean by that is, let's say I've got a magnetic field, remember, and this is kind of like a circle idea, so this time let's make it come out of the computer screen at you. Right, so I have this very directed, uniform magnetic field coming out of the screen, but it's not incredibly large to where whatever particle I'm sending in is going to end up in a circle. Instead, it's relatively small. So I send a charged particle, let's say a proton, into this guy, right? Now this is magnetic field and proton. I need to use the left-hand rule. It's positive, right? So magnetic field coming out of the screen, proton going to the right. That means there is a force that's going to be applied downwards, right? There's going to be a force being applied downwards. And so the path of this proton is going to be something like this. It's going to curve inside the magnetic field here. A projectile motion like thing until it exits the magnetic field and continues on with a constant velocity wherever direction it's going at that point in time. So now this leads me to the application of this problem. Tube TV problem. Right? Tube TV. Tube TVs work like this. I've got some large potential difference plate here. Okay. And by the way, this part is what we're going to focus on. That applies a potential difference, right? So I take an electron, because by the way, tube TVs work by particle accelerators. It takes an electron, accelerates it up to very high velocities towards the screen. Whenever it hits the screen, it hits an exact precise pixel on the screen, causing that color to light up. That's why with tube TVs, if you go over and touch the screen, you'll notice that it's very staticky. That's because there's actual electrons being shot at it, hitting the screen, and then causing those pixels to light up. But anyway, a potential difference here. So let's say I have a big negative plate, right? So that causes some voltage here, right, and some other voltage a little ways off. And so between the two, I have a delta V, right? And I put a electron, negative charge, and I allow it to run away, picking up some velocity. Now this is a part of the problem. I just want to point this out in the beginning part, just to get us the idea. We get, by the way, voltage here, and we're going to have some velocity. Let's actually write it out because we had trouble in the last test. We had trouble in the last test with the difference between voltage and velocity. So, velocity picks up speed as it goes. If we wanted to calculate that velocity, remember this would be work equals negative q delta V, right? And this work is going to be kinetic energy, and that's going to be 1/2 mv final equals negative q delta V, right? Because the initial we assume is 0 whenever we release the electron, so we can calculate the speed of the scale. Now, in this problem, I don't want to worry about that part. I'm just going to go ahead and tell you the electron is coming at it at 3.2 times 10 to the 5th meters per second. So I got an electron that is flying, an electron now flying that way at that velocity. Okay. It encounters a very directed magnetic field going upwards. So in other words, what's happening here is I have a couple of magnets now. Okay, I got a couple of magnets here. Okay. So and then I have a magnetic field like up, like this, with strength B equals 5.8 microtesla. So that'd be 5.8 times 10 to the negative 6 Tesla. So a very weak magnetic field, but this electron's going very, very quick. So do remember that. Also, an electron has very low mass, so because of that, it's going to end up having a small force applied to it. It's going to actually make it move a very long ways. Okay. I want to know, I've got some screen out here. Now you have to remember, what I'm drawing is just this two-dimensional TV screen here, right? But it's not two-dimensional. it's a 3D object, right? This screen is not only that flat piece, but it's also extending into your computer screen and out of your computer screen towards your face. So please try to imagine that. But this is just kind of a side view. We could also get behind this and kind of look over, kind of like if you put your head over where it's running parallel, like you're looking down the computer screen. The screen would actually go outwards from it, so extending perpendicular, if you will, out here. So coming out at you, right? The screen continues to come out, and then it also goes in there also. So this screen isn't just a 2D object. So that's critical to remember, because what I expect to have happen here, if I use left-hand rule, excuse me, I need to use my right hand, right? It's a positive charge. I have magnetic field going up. I have an electron going over towards the right. I expect there to be a force, right? I expect the force to be going into the board. So the electron is going to go into the board, and it's going to fly over and hit the screen. Now, pictorially, what's happening here? Let me take a top view. That was a side view. A top view of what's going on here. I have some magnetic field, right? I have some magnetic field, and the electron is going to fly in and then curve, because the force is applied, right, and hit the screen at some location. And let's assume that the screen is immediately following the magnetic field. The magnetic field goes all the way up to it. My question to you is, if we shoot the electrons at the center of the screen, what distance away from the center of the screen does the electron finally hit? S. What displacement, what distance away from the center of the screen does the electron actually finally hit here? So if I'm thinking about this right now, what I need to realize is this is projectile motion, right? It's just not gravity pulling it down. It's getting pushed up. And I'm looking for S here. So let me try to work this backwards in our heads. What causes this electron to be pushed upwards from this picture on this top view here, right? And this would be a side view up here, okay? What causes this electron to be pushed from our perspective and from that side view into the board? Well, the magnetic force, right? The magnetic force causes an acceleration. So if I can figure out the magnetic force, right? If I can figure out the magnetic force, I can figure out the acceleration on the electron. Then I can use that acceleration. To figure out where it's going to hit kinematics. So that's kind of the sketch of where we're going here. So now let's go ahead and let's start setting it up. First off, what force does this electron experience? Well, it's going to experience force, Q, V, B, and the sine theta, let's assume that it's going in at 90 degrees, right? So theta doesn't matter. So Q, V, B, right? And so that's the charge of an electron. And if you don't mind, I'm going to leave this right now. I guess we'll go ahead and get numbers. That'd be 1.6 times 10 to the negative 19th times the velocity we said from up here, 3.2 times 10 to the 5th, right here. So 3.2 times 10 to the 5th meters per second times the magnetic field strength we said of 5.8 times 10 to the negative 6th Tesla. Right here, B. Okay, microtesla meaning times 10 to the negative 6th. All right, so we punch that into our calculator and we get the force being applied on the electron. All right, we come out with force of 2.97 newtons, 2.97 times 10 to the negative 19 newtons. Now that seems like a very, very small force until once again we remember an electron has a very little mass, so whenever we try to get to the acceleration here, F equals ma, right? F equals ma, so my 2.97 times 10 to the negative 19th is equal to the mass of the electron, 9.11, times 10 to the negative 31st, times A, divide both sides by 9.11 times 10 to the negative 31st, we actually get a pretty large acceleration, about 3.26 meters per second squared. Now that's a relatively large acceleration right there. Now, here's what I've got to do next. I have to come back up here, and I need to give you a distance up here. The average depth, and we're just going to take a depth of a 2TV, we're going to say that this distance right here that the magnetic field covers, okay, all the way to the screen, is somewhere about 45 centimeters, about 45 centimeters, okay, about 45 centimeters. Now that we have the acceleration, we have the distance, this becomes a projectile motion problem, where the force of gravity isn't what's doing the pulling down. Instead, it's the magnetic force that's acting as the force of gravity, which we have calculated and gotten a magnetic acceleration. Except I miswrote there. That's not 3.26 meters per second squared. That's 3.26 times 10 to the 11th. That's kind of critical here. Times 10 to the 11th. A very large acceleration, not just 3.26 meters per second. 3.26 times 10 to the 11th. It would be the acceleration. Small force, but even smaller mass gives me a very large acceleration here. Let me remind you of projectile motion again with gravity, right? I have a cliff. I throw a ball off the cliff at some velocity, a horizontal launch, right at the sine of 9 degrees. If we were thinking about QBB sine theta sort of deal, that's all we have to do with a horizontal launch, right? It comes down like this and it hits the ground, right? And then we divide it up into our x and y axis, right? And the x-axis, it was constant velocity, okay? And I'm going to go ahead and start, I'm going to go ahead and scratch x and y axis. I want to put in here, I want to go ahead and put in here some other terms, if you will. I'm going to put a forward, okay, forward, and I'm also going to, for the x-axis, and for the y-axis, I'm going to put in to the side, right, the side being down here, The reason I want to do that is because our axis in the previous problem aren't going to be x and y necessarily, depending upon how we call it, but the electron in one axis is just trying to go forward, another axis is getting pushed inwards towards straight towards the side. Okay? And then we realize that the x-axis is just constant velocity, right? It had some initial velocity, right? Equals blah, blah. And if I set this to be 30 meters per second, right? This would be 30. It travels some distance here, right? Well, let's set this at 200 meters. So my x here is 200. And I don't know anything about time. Right, I don't know anything about time. Let's say the goal of this problem is to find the height of the cliff, right? And I know the acceleration of gravity. That's the acceleration. The force is causing, right? It's 9.8 meters per second squared. I can assume the initial velocity, u, in the y-axis is 0. Don't really care too much about the final velocity here. I don't know the time. Right, I don't know the time, and I'm looking for y. And so here conceptually, I don't want to go through all of this right now. We said, hey, use the constant velocity equation, v equals x over t, to solve for time, and then take that time and plug into the y-axis. That'll allow you to solve for the y displacement. Y equals ut plus 1/2 a t squared. Now I know that was all the way from the beginning of the year, but that allows me to solve for the displacement of the object. But we're going to use the exact same principle back here. So coming on back, right? Remind you of the problem. 2dV, magnetic field, the electron goes through it. When the electron goes through, the magnetic field here, caused by these magnets, right? There's a force being applied. We use the left-hand rule, except it was negative, so we used the right hand, of course, and found the force would be going into the screen. Now that force is going to cause this electron to go in a projectile motion. The length of the field, we said, was 45 centimeters. It was 45 centimeters. So let's come down here and let's set up some projectile motion ideas. The straight towards the screen. So I'll label it towards screen, if you will, straight. Okay, the straight towards the screen. That's what you're seeing up here on the side, right? I'm going straight towards the screen. There's a displacement of 45 centimeters. There's nothing accelerating the electron towards the screen, so it's going to go at a constant velocity, right? And so we know that velocity up here. Sorry, let me come back up. We know the velocity, 3.2 times 10 to the fifth, and we know a displacement, 45 centimeters. So displacement, we'll call that S equals 45 centimeters. That's 0.45 meters. A velocity, which we said was 3.2 times 10 to the fifth meters per second, and we don't know anything about time. Now, the part where it's curving, here in the top view, this is the part that's called where it's curving off, right? Where it's now beginning to curve upwards here, okay, from this perspective. Or from the side view, it's beginning to curve into the screen. So I'm caring about from the side view, the curving into the screen, the axis that would go into the screen, like through the computer and back out the computer towards your face. Okay, so we'll call that towards the side. Okay, we'll call that towards the, we'll call that to the side, right? For now, so I don't have to label an X, Y, and Z axis here. I know an acceleration. I know what's called the acceleration causing the particle to turn now. We just calculated 3.26 times 10 to the 11th meters per second squared. I can assume the initial velocity in this axis is 0. I'm looking for, I'll go back and I'll label this Y. I'm looking for the displacement, right? How far away it was that it hit the screen. Let me come back up to the side view and see what I actually labeled this. Here, right here, I labeled it S here on the top view. But down there, I'm calling it Y. Okay, down here, I'm calling it Y question mark. How far does it bend before it hits the screen? So I'm looking for Y, and I need the time to be able to figure that out. This works just like a projectile motion problem. Okay, let's find time from the straight axis, if you will, and plug that into the time for to the side axis. Well, over here it's constant velocity. V equals S over T, right? So that's 3.2 times 10 to the fifth equals my S, 0.45 divided by the time. So solve for the time and then plug into the other axis. Okay, so I come out with a time of about 1.41 times 10 to the negative 6 seconds. A very short time. I mean, goodness gracious, it's going very fast, right? It's going very fast through 45 centimeters, a very, very short distance. So I can take that time and I can plug it in over here, 1.41 times 10 to the negative 6 seconds, right? And now I've got enough information here with the A, the initial velocity, the acceleration, the initial velocity of the time, to be able to solve for how far it is with my Y equals ut plus 1/2 AT squared kinematics equation. Okay, so whenever I plug everything in here, right, initial velocity is 0, so this entire thing goes away right here. So my Y is going to equal 1/2 times my A, 3.2 times 10 to the 11th, times my time, 1.41, 10 to the negative 6 squared, and that will give me a displacement of about somewhere around 3.2 meters, or 32 centimeters. So the electron is pushed 32 centimeters from our perspective into the board where it hits. And that's how tube TVs work. They use large electromagnets. They use large electromagnets to change the magnetic field, okay, to change the magnetic field strength. And the stronger the magnetic field, the farther the electron's going to get pushed one way or the other. And then they reverse the magnetic field to push the electron, for our example, out of the board, right? If it's going up, it's being pushed into the board. If it's being pushed out of the board, then the magnetic field must be going down. There's also electromagnets on the sides that can cause the electron to go up or down. And the combination of changing the magnetic field strength and changing the direction of the magnetic field, and those four magnets there are what allows a tube TV to very accurately paint the electrons onto a screen to give you a picture, painting pixel by pixel by pixel, shooting electrons to where it hits each individual pixel, one thing at a time. Okay? So that's the idea. So in this case right here with this magnetic field strength, the electron had flown about 32 centimeters whenever it hit. Let me remind you, the advantage behind these videos is you can go back and you can re-watch at any point in time you so choose. So please go back, check back through this, watch back through it, take more notes, try to understand it. I understand that, I know that this wasn't the easiest concept to grasp, but if you give it a little bit more time, going back through it a few times, you should be able to get it. We'll talk about it in class and bring me any questions you have.